This video is regarding isotopes and radioactive decay. Let's have a quick look at the structure of atom, which we have already seen. Most of the atom is empty space occupied by electrons, or we can say that the nucleus is in the center with the positive protons and neutrons which have no charge, and there is a cloud of electrons around the nucleus. Protons have a positive charge, neutrons are electrically neutral. Protons and neutrons are also called as nucleons because they are found inside the nucleus. Nucleons are almost identical in mass and size. Electrons are much lighter and smaller than nucleons, and therefore we even do not consider, when talking about the atomic mass or mass of an atom, we do not even consider the mass of electrons. Nucleus is very small, but it contains 99% of the mass of the atom. Let's have a look at how an atom is written as per its mass number and number of protons. So X is representing the chemical symbol of the element. For example, carbon, for carbon we write C, for lithium we write Li. So this X is the chemical symbol for the element. Here written A, it's mass number or atomic mass. How to remember it? A for addition. Addition of what? Addition of number of protons and number of neutrons. All right. So that in total gives us the mass number. This Z at the bottom of the X is number of protons, also known as atomic numbers. All right. So this is how an element is written in form of its mass number or atomic mass and its atomic number. All right. Please do not get confused. The topmost A is the total number of neutrons and protons, and the bottom one Z is only the number of protons. For example, helium. Helium He is the chemical symbol. 4 is the mass number. That means it has 2 protons plus 2 neutrons. Therefore, in total 4. And the atomic number, that is how many protons it has, that is number 2. All right. In some books, these 4 and 2 can also be written on the right hand side of the helium. But you should always remember that the top one is the mass number and the bottom one is the atomic number. Mass number is also sometimes known as atomic mass. Now, what are isotopes? Atoms with the same number of protons belong to the same element. Element is like carbon, nitrogen, lithium, helium, like that. Those are elements. The number of neutrons does not affect which element the atom is. It's only the number of protons that determine which element it is. Okay. Number of neutrons does not affect. Why? Because neutrons, they do not chemically affect the atom because they are electrically neutral. Okay. However, they do affect the mass of the atom. Okay. So the more the number of protons and more the number of neutrons are in a nucleus, the heavier and larger it is. Isotopes of an element share the same number of protons but have different number of neutrons. For example, carbon 13, carbon 14, they have the same number of protons, but their mass number is different. Okay. Isotopes have same chemical properties. Why? Because their number of protons are same. Okay, but they have different physical properties such as density and volume. Why? Because their number of neutrons are different and therefore their atomic masses are different. Proper definition of isotope is that isotopes are variations of chemical elements that have the same number of protons but different number of neutrons. We identify isotopes based on their mass, whereby the sum of protons and neutrons equal the mass of the isotope. Okay. For example, look here, isotopes of hydrogen. Protium, the first one, it has 1 electron, 1 proton, and zero neutrons. Okay, so its mass number is 1. 1 plus 0, 1. Second one is deuterium. It has 1 electron, 1 proton, 1 neutron. So its atomic mass or mass number is 2. This is tritium. 1 electron, 1 proton, 2 neutrons. So its mass number is 3. In all the 3 isotopes of hydrogen, you can see that the number of proton is the same. The thing that is changing is the number of neutrons, and therefore atomic mass or mass number is different. Okay, so always remember isotopes, number of protons same, number of neutrons different. Okay. Now, here is a question. Molybdenum, the atomic number is 42. Atomic number is the number of protons, and atomic mass is, let's say, approximately 95. Now, what I have shown you earlier, they have written just the opposite of it. So don't get confused that on the top, they have written atomic number. In the bottom, they have written atomic mass. But thankfully, they have labeled it. So it's okay. All right. We have to find out the number of protons, nucleons. Nucleons are both protons and neutrons. Okay. And the number of neutrons in this isotope. So by just looking at it, I can tell you that the number of protons is the atomic number. Therefore, it's 42. Atomic mass is total number of protons plus neutrons. So 95 is the number of nucleons. I'm just rounding it off. Okay. Now to find out number of neutrons, what can we do? 95 minus 42. Because 95 is the total number of protons plus neutrons. Out of that, we already know the number of protons. So by subtraction, we can find out the number of neutrons. Here it is. You can pause this video and have a look how I have done it. Okay, now let's have a look at revision of isotopes with this YouTube video.
All atoms of a particular element have the same atomic number. This means that they all have the same number of protons. But sometimes you can find heavy atoms of a particular element. These atoms have a higher mass number. The mass number is equal to the number of protons plus the number of neutrons. We can ignore the electrons as their mass is so tiny. If the number of protons always stays the same in a particular element, and we are ignoring the mass of electrons, it must mean the number of neutrons is causing the difference in mass. Atoms of the same element with a different mass number are known as isotopes. They are defined as atoms of an element which have the same number of protons but a different number of neutrons. If we look at carbon and nitrogen, are they isotopes? They have different mass numbers, but they also have a different number of protons. Therefore, they are not isotopes. They are completely different elements. Different isotopes of elements do not have separate positions on the periodic table. They occupy the same spot because they have the same number of protons. What about carbon-12 and carbon-14? Both carbon-12 and carbon-14 have the same atomic number, which means they have the same number of protons, but they have different masses. Carbon-12 has a mass of 12 and 6 protons. Remember, mass number equals protons plus neutrons. So we can rearrange this formula to give us neutrons equals mass number minus protons. 12 minus 6 equals 6. Therefore, it has 6 neutrons. Carbon-14 has a mass of 14, but it still only has 6 protons. Mass number equals protons plus neutrons. Rearrange. Neutrons equals mass number minus protons. 14 minus 6 equals 8. Therefore, carbon-14 has 8 neutrons. Carbon-12 and carbon-14 are not the only examples of isotopes. There are many more, such as hydrogen, deuterium, tritium, and chlorine-35 and chlorine-37. Isotopes only differ in their number of neutrons and their mass. Their chemical properties are exactly the same because neutrons have no effect on an element's chemical behavior. This is controlled by electrons, which we will discuss in another video. So isotopes, atoms are the same element with the same number of protons but a different number of neutrons. They have different masses, but their chemical properties are exactly the same.
Now we come to radioisotopes. Most of the atoms that make up the world are stable, all right? But there are many naturally occurring isotopes that are unstable. What do we mean by an unstable isotope? An unstable nucleus may spontaneously want to become more stable, and when it wants to become more stable, it will emit a particle and as a result change into a totally different element or isotope. All right? Unstable atoms are radioactive. An individual radioactive isotope is known as radioisotope. If an atom is radioactive, it will spontaneously emit radiation from its nucleus, either in the form of particles or EM light or energy. Okay, so if a nucleus is unstable, in order to become stable, it will spontaneously emit some particles and will completely either change into a different element or it will turn into its own isotope. Okay, example of radioisotopes. Carbon has two stable isotopes, carbon 12 and carbon 30. If I say stable isotope, then these are not radioisotopes. All right. But carbon also has one naturally occurring isotope that is not stable, that is unstable, and it is carbon 14. All right. The nucleus of a carbon 14 atom may spontaneously decay into a different substance, emitting high energy particles that can be harmful. If on any product you see this symbol, then this is the symbol used to label and identify a radioactive substance. Most of the elements found on Earth have naturally occurring radioisotopes, around 200. However, many artificial radioisotopes are produced for medicinal and scientific research purposes using nuclear reactors or particle accelerators. So there are naturally occurring radioisotopes, but there are also many artificially created radioisotopes for different purposes. When you look at a periodic table, I'm sure everybody has seen a periodic table of elements before. So the elements which are shaded in yellow color, they show that they are all radioactive elements. So you can see that many of the elements found in our universe are stable, but there are few which are highly radioactive, which whose nucleus are very unstable. This is the picture of Madame Marie Curie. Scientists such as Marie Curie, Ernest Rutherford, and Paul Willard were investigating radioactive substances in 20th century. Rutherford and Willard found that there were three different types of emissions from these mysterious substances. They named them alpha, beta, and gamma radiation. Fun fact, Madame Marie Curie's body is still emitting radioactive harmful radiations, and therefore it is seal packed under many concrete layers and it's still radioactive, so you can imagine. Now let's look at the three different types of decay: alpha decay, beta decay, and gamma decay. Let's start with alpha decay. When a very heavy unstable nucleus it undergoes radioactive decay, it eject or it may eject an alpha particle. An alpha particle is nothing but it has two protons and two neutrons. Okay, and it is identical to the nucleus of helium. Therefore, either you can write alpha as this alpha, or you can just write 4He2 in the equations. An example of alpha decay is that a parent nucleus of uranium 238, that is an isotope of uranium, When it decays, when it tries to become stable, then it emits an alpha particle, that is 4He2, and the daughter nucleus that is created is of thorium 234 with atomic number 90. If you will closely look at this equation, then you will see that the mass number and atomic number for an equation are always balanced. Okay, so if you see that 238 is the atomic mass or mass number for uranium, then see 4 here for helium, 234 here for thorium. 4 plus 234 equals to 238. Similarly, let's have a look at the atomic number, 92 here for uranium, 2 for helium, 90 for thorium. 90 plus 2, 92. So yes, this equation is balanced. Always the equation will be balanced. This will help you in writing the equations, okay? The energy which is released during an alpha decay is mostly kinetic energy carried by fast moving alpha particle. So this is your alpha decay when a nucleus of helium or an helium atom is released when a parent nucleus undergoes radioactive decay. And this is called parent nucleus and this is called daughter nucleus, the product, one of the byproducts. Okay. Beta decay. Beta decay, there are two types of beta decay, beta minus and beta plus. Let's focus on first beta minus decay. Beta minus decay happens when a nucleus has many number of neutrons and it becomes unstable. Then what happens? One of the neutron, it breaks down, converts into proton. Because now it is converting into a proton, that is a plus charge, therefore an electron is also created and that electron is emitted from the nucleus. Imagine that when a neutral particle is breaking down into a positive particle, in order to balance things, a minus particle will also be created. And that electron is emitted from the nucleus, but the proton that is created stays inside the nucleus. And therefore, the daughter nucleus, the resulting nucleus, it has one extra proton and one less neutron. Okay? In beta plus decay, the nucleus has lot many number of protons and therefore it becomes unstable. So a proton breaks down into a neutron. And because a proton, a plus charge, is converting into a neutron and therefore a positron is created. Positron is emitted from the nucleus while neutron stays inside the nucleus. The resulting nucleus has one less proton but one more neutron. We will have a look at beta minus and beta plus decay in much detail in the next two slides. Beta minus decay. Let's say this is the parent nucleus with atomic number A, atomic number Z, and atomic mass A. The daughter nucleus will have the mass number same A, but the protons will be one more. An electron will be emitted, that is also known as beta minus, and an antineutrino is created. Antineutrino has no mass and no charge. Okay, a neutron is, let's say, lost, so an antineutrino is created. But this antineutrino is massless. It has no mass, zero mass, and zero charge. All right, let's have a look at beta plus decay. The reverse process to normal beta minus decay is happening here. A proton converts into a neutron. While converting into a neutron, a positron is created because when a proton converts into a neutron, the plus one charge has to remain somewhere in the universe. It cannot be just lost in becoming a neutral particle. So that plus charge converts into a positron. A positron has the same chemical properties as an electron, but its charge is positive of that of the charge of the electron. And a neutrino is made. Now, this time not an antineutrino, but a neutrino is made. And this neutrino is also chargeless and massless. So this is the equation when a proton converts into a neutron, a positron or a beta plus decay happens. Okay. Gamma decay. Gamma rays have no mass and no charge, and they travel with the speed of light, that is 3 times 10 to the power 8 meter per second. Okay. When a radioactive isotope emits an alpha or a beta particle and it undergoes a radioactive decay, then the daughter nucleus that is created, it has excess energy and it is in its excited state. You can see here then this asterisk sign, this denotes that the nucleus is excited. And we all know that when something or a nucleus or an electron is excited, it has to come down to its ground state. It has to release that extra energy, right? And therefore, when the protons and the neutrons in the daughter nucleus, they rearrange slightly and they just release this extra energy. They release this energy in the form of gamma rays. All right. So this was about alpha, beta, gamma decay, about radioisotopes, what are isotopes, and a quick revision of the structure of atom. Thank you.